Hey folks, this is Gavin Jones here to talk to you about debugging. Today our objectives are to describe a systematic process of debugging so that you have an algorithm that you can follow to fix the errors that you find in your code. I'm also going to describe for you some debugging anti-strategies. So these are like some red flags you can look out for so that if you identify them, you know you're not debugging well. And then lastly, I'll show you how we can use our simulator to debug effectively and fix our erroneous code. So let's get started. Debugging is the process of finding and fixing errors in our code. This is tantamount to finding and fixing errors in our thinking. Brian Kernighan has a famous quote where he says, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it, which can be interpreted really pessimistically on the one hand. I choose to interpret it very optimistically, which is Brian Kernighan's telling us that the process of debugging is the process of getting smarter, of the process of learning stuff that we hadn't known before. So to me, fixing our code means fixing our thinking. And so to me, at least, when we debug really well, we eventually get this aha moment where we figure out something that we hadn't known before. And the payoff for doing that is that we're better able to predict the way the system's actually going to work. We're able to write better code and to design computers that are much more effective and much more efficient. Debugging, the process of it is very much like being a detective. There are a lot of great resources out there that will elaborate more on what the debugging process looks like. And I'll share some with you towards the end of this video. But if I had to really simplify it, I would say that there are effectively just a couple of things that the debugging process is trying to do, which is answer just a couple of questions. Number one, what's the system supposed to be doing? If we can't identify what is, or we can't describe what's actually supposed to be happening, what value is supposed to be in register, or which instruction is supposed to be executing at this point in time, then really we don't even know if what we're looking at is an error of any kind. We kind of have to know that to start with. And then once we can be able to describe in our own words what should be happening, step number two is to answer the question, okay, what exactly is happening when this bug is occurring? And that goes beyond just saying, this program is supposed to run, but it isn't, or something like that. We want to try to gather as much data as we can as to, okay, I know that this value is incorrect. Well, what else about the system, is slightly wrong or unexpected or incorrect? Because those are going to give you clues as to what is happening in the system. And then once you've spent some time kind of gathering some information as to what the system's supposed to be doing and where it's deviated from that. Step number three is to say, well, what's a likely reason for that error to be occurring? You want to go for if you can, the likeliest reason, but don't get hung up at this stage on spending a lot of time coming up with a great hypothesis. The goal of this step is just to come up with what the evidence generally points to as what might be an error. And once you come up with a reason or a thought as to what the error might be, then you'll apply that test. You'll change a piece of code to see if your hypothesis is true or not. And so if your hypothesis is that, well, my program didn't work because the user typed in a value I wasn't expecting, then you'll test that. You'll rerun your program. Under two conditions. You'll rerun it with the incorrect input, and you'll verify that you sort of found yourself with the same error condition, and then you'll rerun the same program with what should be a known good condition and confirm that in fact the program works as expected. And if that's the case, then you've got some confidence then that your fix solved the problem, that the error was as you hypothesized a step previously. But you might find out that when you rerun the test with some bad input, that you get a different error, or that the machine didn't behave in the exact same way as you saw appear in sort of steps 1 and 2. And you might find that even though you give the program known good input, it still doesn't work correctly. In which case, you haven't fully solved the problem. The fix didn't exactly work, so it's not necessarily a bad thing. What that amounts to is additional information. It's information as to other ways in which your program might be operating incorrectly that will inform a better hypothesis. And so that means that you need to circle back to somewhere in these 3 steps. Initially maybe just coming up with a different reason and testing that. But if enough of your hypotheses, enough of your tests fail, then you might need to go back to these first couple of steps and ask yourself again, okay, what's going on? What's what should be happening to try to come up with a more informed hypothesis. And ultimately, it's this process of sort of gathering clues, hypothesizing as to what might be an explanation for why the system is not performing correctly, and testing until you get to a solution. That's the process of debugging. Once you found your solution, though, you're not quite done. We'll look at in just a couple of minutes what are some additional things you can do to help kind of close the loop on your debugging and make the most use of this whole process. But for the interim, I want to share with you a couple of anti-strategies to be on the lookout for. So one anti-strategy is something I'll call the Feynman solution. Richard Feynman, is a brilliant physicist who famously said at one point that when he needs to solve a really difficult problem, what he does is he sits down, he thinks really hard, and then he writes out the answer. And so Dick Feynman might be a brilliant enough person for that to work for him, but for the folks like us, it's probably insufficient. And so if you ever find yourself just sort of not following a process, just sort of sitting and thinking and speculating, then that's a red flag that you're not being deliberate and you're not being efficient in your problem solving. Another anti-strategy here is you might call it the hack and slash, or you might also call it the guess and check. This is where something's going wrong, and I haven't taken the time to really stop and ask myself, what is a likely hypothesis for this problem. I've just sort of, I think to myself, well, I don't know, I'm going to change this piece of code and see what happens, right? I think the error is over here, regardless of what the evidence tells me. So I just start, changing big pieces of my code. I start just editing stuff, even though I have no idea if the error is actually in that location. And so again, that's also not following a deliberate strategy. And the problem with these two approaches are that they result in, number one, very brittle code. If I haven't actually stopped to figure out what is the cause of this error, then even if I apply a fix and it seems to work, I have very little confidence in the fact that code is not going to break in the future. And I end up having pieces of my code that, with little comments that basically say, well, I can't change this because it works when it's in there and it doesn't work when it's not, and I don't know why. So this results in very brittle code and a complete lack in confidence in the fact that, our code is going to work at all in the future. One of the things that's even worse than asking, why isn't this code working, is asking, wait, why is this code working? That the fact that it's working and we don't think it should is also a red flag that we don't understand what's going on, and there might be ways in which it breaks in the future, that are surprises to us. So we want to try to avoid these strategies so that we can have some faith in our code, so that we know it's robust, and to do that we need to follow a very deliberate process, kind of like this. Okay, so I'll share with you a couple of additional tips, and then lastly, I'll show you how we can apply these debugging strategies to with our simulator to debug a piece of code. So a couple of tips that have really helped me in my debugging career. Number one, save a copy of the original code, and if you're making changes, make changes to a different copy. And along the same lines, if you can, try to change just one thing at a time. The goal being, when we eventually find our solution, we should be able to go back to the original code that we thought would work and make a very small change to implement our fix and have the code start working. If we are hacking and slashing, then what we might find is that eventually the code does work. We know why, but we are so far, into the weeds, so far removed from our original piece of code that we might need to effectively start all over on solving the problem because we've just lost, what was the original sort of train of thought. So save the original copy, work on a separate copy, and along the same lines, try to change just one thing at a time. Number two, write down what you're doing. What I found is that, this doesn't have to be lengthy or onerous. It can literally just be, a notebook where I jot down, this was the error that I saw. I tried changing register 1 to this value. I got the same error. I tried changing my input to this value, and I got a slightly different error. What I found is that just that, the act, number one, of me writing stuff down forced me to be a little more deliberate, forced me to slow down and actually think about why these errors were occurring. And then additionally, that notebook serves as a great reference in the future. I come back the next day and kind of go, and I might think, oh gosh, I forgot what I did yesterday. But that notebook served as a reference. I could say, oh, okay, this is where I left off. And in a lot of cases, I would think to myself, oh, what I haven't tried is this. I thought I did yesterday, but I forgot to control for this variable. So let me rerun this experiment or something like that. So, so I'd recommend, just as you're debugging, jotting down what's going on. And then periodically, definitely take a little break. The way our brains work is that to debug, you have to be very creative. Your brain's actually most creative when it's not thinking about the task at hand. So, which is a little weird, but the way your brains work a lot of times is that if you are focusing on a task, you're very good at sort of receiving and cataloging information. And so a lot of folks will find it a helpful routine to sit down for no more than an hour or two, really collecting information, trying to categorize and define, spending a lot of time on sort of these first 2 or 3 steps. And if you can't immediately solve it, at some point, getting up and taking a break, go up and use the restroom, grab a glass of water, take a walk outside. And what that does is that lets your brain, shift from the part of your brain that is very good at cataloging and identifying to the part of your brain that's really good at making disparate connections. And what I found in my life is, it felt like a superpower. If I sat down for an hour or two to really kind of work on a problem and nothing was coming to me, almost as soon as I got up to go use the restroom or grab a glass of water, my brain would go, oh, shoot, you know what I haven't tried? Or, I've been totally forgetting this one thing. This, by the way, this is the same phenomenon that it kind of explains why a lot of folks will say they get the best ideas in the shower, because believe it or not, your brains are working on problems even while you're not directly thinking about them. So third tip here is just take a break. It's okay to stand up and walk around or sort of put the problem down for a little bit. Okay, last 2 tips are what to do once you actually solve this problem. So let's say you make it here, the fix works, hooray, you've got a solution. Oops. So number one, once you found the error, it would behoove you to scan the rest of your code to make sure you're not making that same error elsewhere in your code. And also, what I would recommend is, once you figure out the solution to your error, start a checklist of what mistake kind of led to that. And that checklist can form sort of a first stop in the future when you realize something else is happening. You might insert, like here in step 3, in terms of likely reasons. Well, a likely reason for something to occur might be the same reason that it occurred last time. So sometimes you might find that having a checklist of errors you've made in the past is an easy way to kind of confirm that you're not making those same mistakes again. Okay. The last thing we'll take a look at is the simulator. So, in the previous lesson, we saw how to write and run code in the LC3 simulator that lets us, pretend like it's being run on an actual machine. But we kind of gloss over these buttons here. These buttons give us a much finer grained control over the simulated processor, and we can do a couple of the cool things that let us see what the code's doing at a very fine-grained level. So we looked at the play button here. That was going to just sort of ran our code from start to finish. But we also have a couple of buttons here in the middle that allow us to step over instructions one at a time. So we've got this little arcing arrow, which will step over one instruction. If we click that button for each time we click that button, the simulator will execute a single line of code, which can be very useful. That's the main one we're probably going to use to sort of step one instruction at a time in our simulator. But we can also use the step into and the step out of buttons once we learn a little bit more about subroutines. The step into button will will follow us into a subroutine, whereas the step over button will sort of skip over a subroutine based if we're looking at a piece of code. Step out says if we're in a subroutine, then we'll automatically finish that and jump back to where the the subroutine goes back to sort of the main code. Additionally, we can use these little stop sign with the exclamation points on our memory to set a breakpoint. A breakpoint means that when we hit the run button, we won't actually run our program all the way to the finish. Technically, what this run button does is run until the program's halted or you reach a breakpoint. So this can be very useful, to sort of skip over big chunks of code. We can set a breakpoint after where we want to kind of skip over, hit the run button, and then our processor will halt right at that breakpoint. Or maybe we set a breakpoint inside a loop. So we can hit run and just sort of halt at the same place inside our loop every time. And that can be useful for kind of seeing how values change as a loop iterates. And then lastly, we can actually hand edit these values. We can actually go in here and change register values to sort of change as our program is executing, or at least when it's paused. We can change values to see how our program changes based on different inputs. So let's take a look at how that might work for this program here. This is the first debugging example from our textbook, section 6.2.2.1. So we're trying to multiply these two values, but we get an error. So if I go to my simulator here, and let's say I were to reload my code. Actually, let's do this, reload. And then if I were just to run this code, I would see that it looks like the value of multiplying 5 by 4, I get 25, which is clearly incorrect. So I'm going to employ some debugging strategies to sort of, figure out what's going on. If I were to look at this enough, one thing that would kind of jump out at me maybe is that the R5, which is the value I'm sort of subtracting from to count how many times I add this value to itself, is 65,535 or FFFF. And if I'm thinking about 2's complement numbers, I might recognize that this is the value of -1, and that's a little odd. So so I got some clues here. I'm going to try to continue on by setting a breakpoint here at the sort of the bottom of my loop. Okay, so I've clicked the stop sign to set that breakpoint, so now if I reinitialize and load, I can see my program counter up here. When I click the run button, it'll skip through these instructions and pauses right here on this breakpoint. So I can see that R2 has the value 5 because that was added here in this add instruction. I've subtracted 1 from the other value here, and I'm halted on this branch instruction. So so far so good, looks okay. I'm going to hit run again. 5 got added to 5, so that was 10, and I subtracted 1 more from 3 to get 2. Okay, so far so good. If I hit run one more time, 5 plus 10 is 15. 1 more is subtracted from this value, so that's fine too. If I hit run one more time, I get the result I thought would be the value multiplying 5 by 4, and R5 is 0. So at this point, I should be able to step over 1 instruction and halt the process. So if I click my step button, that actually doesn't happen. I thought that after this should have come the halt, but instead I took my branch, and this might be the thing that sometimes we call the smoking gun. We go, okay, when R5 was 0, I should have ended my loop, but in fact I took one more iteration. And if I were to step over this line at a time, okay, that's where I get my 25. I subtracted 1 more. That's where my -1 came from. And now I finally go to my halt instruction. And with this smoking gun, I might be able to realize, oh, my branch was malformed. Here I'm branching if the result is positive or 0. And the way I had formulated my loop, really this should have just been branching only if the result was positive. As soon as it was 0, I should have exited that loop. So this should be branch if positive, not branch if 0 or positive. So these single step buttons, the breakpoints, can be very useful in debugging code. I'll show you one more if I reload my code. One more thing I can do. I can actually change the values here. So I'm gonna step through my code, I'm going to skip over a couple of loops to get to this point here, where let's see. I think this. So this is the point where I feel like I should have taken. I should have skipped over the branch, but in fact I took the branch. So if I want to test my hypothesis, then what I might do is change this register to -1 to see if I skip over my halt. I think maybe, yeah. In order that the instruction was executed right before then. So what I'll do here is set my breakpoint one instruction before then. I'll come here. So now 5 and 0. I'm about to execute this or evaluate this branch instruction. Here, if I change my register value to R1, then I should evaluate my branch and then go to my halt instruction. So that might be a way that, kind of going through this, I confirmed for myself, like, okay, you know, I'm exiting my loop after one more loop than I think should be being executed. Okay, so today we talked about debugging, and just the fact that if we're debugging correctly, we're being very systematic about it, and at the end we're getting this aha moment that means we've learned something new about the LC3 that we didn't know before. A very basic process to do that is to ask, what's this? To gather some clues, make a hypothesis, and test that. We want to be cognizant of some anti-strategies, the Feynman algorithm, where we just sort of sit down and think really hard, or the hack and slash, where we are, making changes to our code without any, thought or deliberateness to it. And we took a look at how we can use the single step buttons here, as well as setting breakpoints and even changing values in our simulator to help us figure out what's going wrong with a piece of code. The last thing I'll share with you are a couple of resources. I've got a blog article here called How to Debug, where I drew a lot of this material. That's a quick one, so I definitely recommend you reading that to get another perspective. And then a couple of books that I've either read or are on my list. Debugging by David Akins is a short book. You can get the link here to Amazon or the website here. Great one that talks about how to debug in a very broad context and elaborates on some of the stuff we mentioned today. And then I've got a book here, If I Only Change the Software, Why Is the Phone on Fire? Definitely, if you enjoy little microcontrollers like Arduinos or embedded systems, this is a great one. I really enjoyed it. It's set up almost like a whodunit, like a mystery. So each chapter kind of gives you the clues you need to solve the problem, and your goal is to try to figure it out before the author reveals the secret. And a couple other debugging books that are on my Amazon list that I've been recommended to in the past. All right, that's all for today. I'll see you next time.